Hello students. In the today's lecture, we will take the next case to identify the principal stress and principal planes. And in this case, we have, apart from the normal stresses, biaxial state of stress, which we have considered in our last lecture, sigma x and sigma y, there is a shear stress also acting on the system. Okay, so in the last lecture we had the case, first case was when there is only uniaxial stress, that means sigma x was acting alone. In the second case we took there was sigma x and sigma y, both were acting on the body. Now in this case, not only the sigma x and sigma y, apart from that there is a shear stress tau xy also acting on the system. As we know that the shear stress is a complementary in nature, so that's why there is a tau xy pair and then there is a tau yx pair, both acting on the this block. This block is of let's say length L, the height is B, and the depth of this section is T. Now we want to determine the value of the stresses on an inclined plane. So that inclined plane we have taken is as BE. So this BE is the inclined plane and it is inclined at an angle theta from the normal. Now let's draw this wedge shape portion of this block BCE separately, and let's draw all the applied stresses on it. So the sigma x, sigma y, and tau xy, tau yx are shown here, which are acting respectively on BC and CE part of this block. And we want to determine the stresses on the inclined section BE. So this inclined section is having the normal stress, we are referring it as sigma theta, and the stress which is acting along this BE is termed as shear stress tau theta. We are as we want to resolve the forces, so we need to convert these stresses into the forces. So the corresponding forces that will be acting because of these stresses are shown in the next figure, the third figure. So you have the force Px acting because of the stress sigma x acting on the BC surface. You have the force Py acting on the surface EC, and you have the tau Q1, the shear force acting because of the shear stress tau xy, and the shear force Q2 acting because of the shear stress tau yx. Similarly, on the plane BE, because of the normal stress sigma theta, there will be normal force Pn, and because of the shear stress tau theta, there will be normal force the shear force Pt will be acting, or tangential force will be acting on it. Now from figure second and third, let's express first the forces with the help of stresses and their corresponding area. We know that the force is equal to stress times area, so let's start it using that formula. So we have the shear force Q1, which is shown here. So this is acting on the surface BC. So the area on which it is acting is the BC multiplied by the depth of the section, that is T, the thickness T of this block. As we know that the BC is nothing but the width of the section, which is shown here B. So you substitute for BC as small b. So you get Q1 equal to tau xy into B into T. Now the next force is Q2, the shear force Q2. The stress, corresponding stress is tau yx, and the corresponding area on which it is acting is distance CE multiplied by the depth of the section small t. The CE can be expressed in terms of BC, because this angle is theta here. I have not written here in this diagram, but this angle is theta. So CE by BC is equal to tan theta, and BC is equal to B. So CE by B equal to tan theta. So CE will be nothing but equal to B times of tan theta. So let's substitute it over here. Now let's talk about the force Px, and the force Px will be equal to the corresponding stress sigma x acting on the area BC into T. Okay, so BC is equal to B, so again sigma x into B into T. Similarly, Py will be equal to the corresponding stress sigma y multiplied by CE into T. C is B tan theta, so you get this expression as here. Now comes the turn of the forces which are acting on the inclined plane. They are Pn and Pt, and let's express them in terms of their corresponding stresses sigma theta and tau theta, as they are acting on the surface Be multiplied by the depth of the section T. So we have expressed them as sigma theta times of Be into T. Now this Be can also be expressed in terms of Bc, because we know that Bc by Be is equal to cos theta. So that's why you can write it B as B by cos theta into T. Similarly, you can express the PT also. So what we have done in this first 6 equation, we have actually expressed the forces in terms of the corresponding stress values which are given to us and the corresponding area. Now, as we can resolve the forces, so for the equilibrium of wedge BCE, let's resolve the forces in the normal and parallel direction to the BE. So first let's resolve the forces normal to the BE. So on this side you have the force Pn acting on this, which is normal to the BE. On the other side, the balancing forces which are acting are the applied forces. So you have Px here, so which you can see extend here. This is the acting at angle theta to the Pn. So there will be component of Px cos theta here. Similarly, you have the force Q2 also acting in the same direction as Px. So again, you will also get the value as Q2 cos theta. Then next force is your Py, and Py is acting at an angle of 90 minus theta from the Pn. This angle is 90 minus theta. So you have Py sin theta here. And similarly, because the Py and Q1 are acting in the same direction, so Q1 will also come with the sin Q1 sin theta. So this is how we get the resolution of forces in the vertical direction. Now we are going to substitute the equation 1 to 6 in equation 7. So once we substituted these into this equation and you simplify the term, you are finally going to get this expression as shown here. So sigma theta will be equal to sigma x cos square theta plus sigma y sin square theta plus 2 times of tau xy sin theta cos theta. We will use the relation from the trigonometry. We will express cos square theta and sin square theta in terms of cos 2 theta, and 2 sin theta cos theta is sin 2 theta. So this will give us values of sigma theta as shown over here as equation 8. So this equation 8 is giving us the relationship between the normal stress to the plane, inclined plane, which is at angle theta, with the applied stresses sigma x, sigma y and tau xy. So if you know the value of the applied stresses, which are sigma x, sigma y, tau xy, you can find the value of stress acting normal to any inclined plane which is inclined with an angle theta. Okay, so this is what this expression is about. Similarly, we can resolve the forces in the parallel direction of the BE, and if you see again that figure, you will see that if the PT is acting in the direction of BE, so if you resolve the force Px, it will be acting at 90 minus theta angle to the B. So that's why there will be Px sin theta component as well as Q2 sin theta component will be appearing. And because Py and Q1 are acting at an angle theta with the surface BE, so there will be appearing with the cos theta terms. So Q1 cos theta and Py cos theta terms will come. But as they are acting in opposite direction, so there will be negative sign preceding these values. So this is what is shown over here in the expression 9. So in the equation 9, you can see that the Px and Q2 are coming with the sin theta component, and Q1 and Py are coming with the cos theta component with a negative sign preceding them. Again, we will substitute from equation 1 to 6 the values of Px, Q1, Q2, Py and Pt and in the equation 9, and finally after simplification you will get this expression of tau theta as sigma x minus sigma y by 2 sin 2 theta minus tau xy cos square minus theta minus sin square theta, which we express in terms of cos 2 theta as equation 10. So finally equation 10 will give us the amount of shear stress or the stresses acting parallel to the inclined plane in terms of the applied stresses sigma x, sigma y and tau xy. Now we need to find the value of principal stresses, and principal stresses are the acting on the principal planes, and we have defined the principal planes are those planes where the shear stresses are 0. So in order to find the location of the principal stress, let's equate the equation tan to the 0 so that we can find the angle at which our principal plane lies. So if you equate the equation tan to the 0, you will get the tangent of 2 theta, which I have put a subscript as p, which is indicating the principal plane, as 2 times of tau xy divided by sigma x minus sigma y. So this equation 11 equation gives you the angle at which the principal planes are inclined with the vertical. Now since tangent of 180 plus 2 theta is also equal to tan 2 theta, this is the third quadrant, so there are two planes which satisfy the above relation, and the value of 2 theta differ by 180 degree for these two planes. Thus the value of theta will differ by 90 degree. So as we have already said that the principal planes are three mutually perpendicular plane, and we have taken only the two-dimensional case here, so that's why we are getting the location of the two planes which are at 90 degree or right angle to each other, and the value is given by the equation 11. Now we can express this tangent of 2 theta as perpendicular divided by base, as I have shown in this figure here. So with this figure you can see that it will be equal to 2 times of tau xy divided by sigma x minus sigma y, where this angle will be 2 theta. So you can apply the Pythagoras theorem and find the value of under root of 6 sigma x minus sigma y whole square plus 4 times of tau xy square here. Now let the two values of 2 theta be let's say the 2 theta 1 and 2 theta 2. The first angle that we define is theta 1, and the second angle which will be at 90 degree to that will be theta 2. So from this triangle, let's first find the value of theta 1. So sine of 2 theta 1 will be equal to 2 times of tau xy divided by under root of sigma x minus sigma y whole square plus 4 tau xy square. Similarly, you can find the value of cos 2 theta 1. Now the other angle is, as we know, is at 180 degree from this angle theta 1, 2 theta 1. So sine 180 plus 2 theta is equal to minus sine 2 theta, and cos 180 plus 2 theta is equal to minus cos 2 theta. So therefore the second angle will give you the sine 2 theta 2 and cos 2 theta 2 value as shown in equation 14 and 15. Now we will substitute these values of sine 2 theta and cos 3 theta from equation 12, 13, or we can use the pair 14 and 15 for angle theta 2 to obtain the maximum and minimum principal stresses. So we will go back to the equation of sigma theta here from equation 8. Here we have in this expression we have cos 2 theta and sine 2 theta. At these places we will substitute the value of sine 2 theta and cos 2 theta for the first angle and the second angle principal plane that we have calculated. So once we do this here, you see here we have substituted the value of cos 2 theta 1 and cos sine 2 theta 1 here from the equation 12 and 13, which are shown over here. You can get the value of sigma 1 as sigma x plus y sigma y by 2 plus under root of sigma x minus sigma y by 2 whole square plus tau xy square. This is equation 16. Similarly, if you use the another pair cos 2 theta 2 and sine 2 theta 2, the other principal stress will come out to be sigma x plus sigma y by 2 minus under root of sigma x minus sigma y by 2 whole square plus tau xy square. You see this will be the higher value and this will be the lower value in comparison the principal stress. And both of them together can be expressed as equation 18, where I have used the sign plus minus here. So plus for the higher value of principal stress and minus for the lower value of the principal stress acting on the another plane, which is at 90 degree to the previous plane. Now to find the maximum value of shear stress that is acting and to find the location of that plane at which it is acting, let's differentiate the equation the equation 10 with theta. Okay, so I have written here the equation 10 we have determined for tau theta as again here. So this is sigma x minus sigma y by 2 divided and multiplied by sine 2 theta minus tau xy cos 2 theta. If you differentiate it with respect to theta, you will get the expression as shown over here, and from this you can find the value of tangent of 2 theta, which I have put the subscript as for the plane where the shear stresses are maximum. This will be given by minus sigma x minus sigma y divided by twice of tau xy. And now again I can represent it into form of a triangle. So because this tangent of 2 theta is perpendicular divided by base as sigma x minus sigma y divided by 2 times of tau xy, I have just dropped the minus sign here. So because there will be two plane, which will be the another plane will be at 180 degree to this plane, so theta will be separated by 90 degree angle. So we can calculate the value of sine 2 theta and cos 2 theta as shown here in the equation 20 and 21. I have used the sign minus and plus minus for the corresponding value of theta 1 and theta 2. Now you can substitute the equation 20 and 21 into the equation 10 as shown here to obtain the maximum value of the shear stress, and the maximum value of shear stress that we get will be given by tau max equal to plus minus under root of sigma x minus sigma y by 2 whole square plus tau xy square. So this will be the maximum value of shear stress, and the angle of the plane at which it is acting will be given by equation 19. So if you know the value of sigma x and sigma y which is acting on the plane, you know the value of shear stress that is acting on the plane, you substitute those values in the equation 19, you take the inverse of that, tan inverse of that quantity, and divide it by 2 to obtain the angle of the plane at which it is acting. Now you must notice that this tau max value is basically half of the difference of sigma 1 minus sigma 2. Maybe you can you can go back to the expression of sigma 1 sigma 2. If you subtract the two values, say of sigma 1 from sigma 2, you will find that it will be twice of under root of sigma x minus sigma y whole square plus tau xy square, and if you divide it by half, you will get the value of tau max. So the maximum shear stress is equal to half of the difference of the principal stress acting on the two planes. Now let's take the case in which only the pure shears are acting. So in the previous case we have the biaxial state of normal stresses sigma x and sigma y. Apart from that, we were having the tau xy also acting on the system. So this is the ABCD block. Again, we are interested to find the stresses on the inclined plane BE. The normal forces are on this plane is Pn and the tangential force is Pt, and the shear force that is acting on the block is Q1 on the face BC and Q2 on the face EC. Okay, now we can either go by resolving the forces as we did in earlier, or we can simply use the expression of equation 8 and 10 that we have obtained in the previous case, where we can substitute for the sigma x and sigma y as 0. So if you substitute for sigma x and sigma y as 0, you will get this sigma theta as tau xy sine of 2 theta, and if you use the equation 10 and you substitute sigma x and sigma y 0, you will get the equation tau theta is equal to tau xy cos 2 theta. You can just simply verify it here. This is your tau theta expression. Okay, so if you substitute sigma x and sigma y both are 0, you will get only this part tau xy cos 2 theta, and this is our sigma theta expression here, equation 8 here, that is. And if you substitute these both components as 0, you will only get the tau xy sine 2 theta. Okay, right? So we can use these expressions of equation 8 and 10 directly and substitute for sigma x and sigma y as 0, and we can obtain the value of sigma theta and tau theta. Now, in order to determine the principal plane, we need to find the plane where tau theta is 0. So you substitute tau theta equal to 0, you will get the cos theta. For that purpose, cos 2 theta should be 0. That means 2 theta value can be either 90 degree or 270 degree. That means theta can be half of it, that is 45 degree or 135 degree. So a plane which is inclined at an angle of 45 degree from the vertical in the case of pure shear will give you the principal plane. Okay, and at this plane, though we are applying the pure shear on this block, there will not be any shear stress acting, only the normal stresses are acting. So this plane which is inclined at 45 degree or 135 degree carry no shear stress, and thus will be called as the principal plane. And at this principal plane, the value of the principal stress sigma 1 can be obtained by using this expression here. And if you substitute theta is equal to 45 degree, you will get sigma 1 as tau xy, and if you substitute 135 degree, you will get sigma 2 as minus tau xy. So the principal stress value will be equal to the applied shear stress value here in this case. In our next class, We will do some numericals on this portion, and we will also discuss about a graphical method of finding the principal plane and principal stresses, that is called as Moore circle. Okay.